Dear all, let's continue video lectures on mathematical analysis 1. So the next topic here is increasing and decreasing intervals of the function, concave up, concave down, and flex points. Okay, so firstly, let's give the definition of increasing and decreasing functions. So when we say in general case it is, and then we will give it using derivatives. So the main idea here is apply derivatives to qualitative study of the function. And to the qualitative study, we need to know here the intervals of increasing, intervals of decreasing, and also we need to know here all critical points and define here extrema points, maximum and minimum, and also using second order derivative we will find here concavity, convexity, and the flex points. Okay, so firstly let's give in general case definition of increasing and decreasing intervals. So given any two functions, given any 2 points, let's say x1 and x2, and they are satisfy the relation, so on the given interval x1 less than x2, if f of corresponding values of the function f of x1 less than f of x2, then fx is increasing on I. For example, let's give any example here. F of x equals to x cubed. And let's draw the graph. And what will be the graph of the x cubed here? So, and the graph, you know, it is this kind of function, but here some incorrectness. So when we draw the graph here, so we have this kind of function. Yes, it is hyperbolical, and to find increasing or decreasing, we'll consider 2 points here. For example, here it is x1, let's say, and here, for example, x2. And now, if we consider the corresponding values of the x1, here f of x1, yes, it will be f of x1. And here we have the corresponding value for the x2, it will be f of x2. So here we have 2 corresponding values of x1 and x2, f of x1, f of x2. And you can see here f of x1 less than f of x2, where x1 less than x2 for all on the given interval. x1 less than x2, the function corresponding value of the function here, f of x1 will be less than f of x2. It means that it is increasing function. And similarly, we will define here decreasing on interval, given interval. So here again, x1 for any x1 less than x2 should be satisfy f of x1 greater than f of x2. So in this case, we call it as decreasing function. So we say that x cubed will be example to the increasing function. It's always increasing. And now let's say let's give the for decreasing function example. So what kind of function we can find here as decreasing? For example, let's say f of x equals to x squared parabola on the given interval minus infinity until 0. 0 is included. So, and here, what will be the graph of f of x equals to x squared? It is this kind of function, you know. But here we need to consider only left side of the parabola, because our interval here is from minus infinity until 0, and the left side of parabola will be like this. Yes, so here we can say that in this parabola, let's draw one more time. So yes, if we draw it fully, we need to continue. And here at the point 0, it has a minimum, yes, a relative minimum, so an absolute minimum also. So, and here it will be now decreasing when it is from minus infinity till 0. It will be decreasing, and we denote it by the narrow down, and increasing function we denote by narrow up. So here you can see on the left side, from minus infinity till 0, it is decreasing, and after 0 until plus infinity, it is increasing. So you can see here full parabola, so x squared on from minus infinity till plus infinity, it is decreasing when from minus infinity till 0, and from 0 until plus infinity, it is increasing. Now, if the function only increasing or only decreasing, we say this kind of function also monotonic functions. Monotonic. So here in the whole given interval, I mean, so here x cubed from minus infinity to plus infinity, it's monotonic because it's only increasing function. But parabola, we cannot say monotonic because of here in the if we consider the parabola, you can see from minus infinity to plus infinity, it's not monotonic because here we have intervals of decreasing and here we have intervals of increasing. So that's why it's not monotonic. But if we consider it separately, for example, only minus infinity till 0, it is decreasing, and you can say it is monotonic on this given interval. Or if you consider from 0 till plus infinity, it's again only increasing, and also you can say it is monotonic on the given interval. But in general case, on R, from minus infinity to plus infinity, you cannot say. Fact. So now, let's consider the first fact. If f prime greater than 0, now using derivatives, we will define increasing and decreasing here. So if f prime greater than 0 for every x on some given interval I, then f of x is increasing. It is increasing on the interval. And similarly, f prime less than 0, so f of x is decreasing. So you can see here derivative, find derivative. To define it is increasing or not, we need to find here derivative and find corresponding inequality. If it is greater than 0, it will be increasing. If it is less than 0, it will be decreasing. If it is equals to 0, what we have? So what does it mean? Derivative equals to 0. It will be only constant. So f of x will be constant. For example, let's say an example here, f of x equals to 2. So in this case, derivative here is, derivative of the constant is 0. So what does it mean? It means that it is constant function just. Now let's consider the first example. Determine all intervals where the following function is increasing or decreasing. Now here we have f of x, given function, fifth degree polynomial here, and then find derivative here, first order derivative, to define intervals of increasing and decreasing. Now, so f prime x here is equals to minus 5x4 plus 10x cubed plus 40x squared. So now let's defactorize this given expression. After factorizing, we have minus 5x squared, x squared minus 2x minus 8. And also we can factorize this one, yes? This quadratic polynomial is here. And then we have the last one. Sorry. So Here we have now, after factorizing, here we have roots when we're equating by 0. When we're equating by 0, here we have the following critical points using previous lectures. So here we have critical points -2, 0, and 4. And now, why we need it? To define here positivity or negative of this function. And now let's consider the following points, critical points, and following intervals here. So when it is, look, here we have 4 and 3 critical points, -2, 0, and 4. So, and now, when we do, for example, find here, let's find how it will be. So it will be -2, it is 0, yeah, and 4. It's like method of intervals when we solve quadratic inequalities. And now, so here, if it is bigger than 4, just put a given function and define here. If it is bigger than 4, what do you have? Here also you can see, so if you put to the derivative, the given function here is now this one, derivative. To the derivative here we have, if you put 5, for example, yes, if you put 5, it will be now, what is it? If you put 5, what kind of values you get here? Here also you have already one. So if you put 5, here we get -875, for example, and which is less than 0. So this is less than 0. So we can put here minus. Because we are considering here this kind of inequality, let's consider here -5x squared, x minus 4, and x plus 2. For example, let's consider greater than 0 or equals to 0. So if we have non-strictly, it will be just increasing. If you have strictly, it will be strictly increasing. Okay, we will check to the increasing. Now, after finding here we have minus, and for the next interval, when it is from 0 till 4, we have here plus sign. Here we have plus sign. And when we move from 0, we'll not change the sign, because here also you can see, if you can check, put -1, for example, from -2 and 0, you get 25, and it's again 0, because of here we have even power. And when it is -2, it is now again minus. So we have the next result. So here we have minus, here we have plus, here we have again plus, and here we have minus. So, and what does it mean? You will check derivative, not given function, first function, you will check derivative. So when you check, you get here minus, plus, plus, and minus again. So, and now when we say it is increase, when they are where increase, where a plus, it is increase. When it is decrease, where minus, it will be decrease. So, and the result here, intervals of increase and decrease here, you can see when it is increase, it is from -2 till 0 and from 0 till 4. When it decrease, it is from -infinity till -2 and from 4 till plus infinity. So this is intervals of increase and decrease of the function. Now, next example. Here is we need to here sketch the graph of the following function, the previous one. So we have find here intervals of increase and decrease. So we have now, and now we'll try to sketch the graph. So and the graph of this function here, we have now intervals of increasing and intervals of decreasing. And you can put here, for example, from here also you can see from -2 and 0, and from 0 till +4 it is increasing. From -infinity till -2 it is decreasing. So you can see here it is decreasing. It's decreasing. And now here it's increasing. Yeah. And here again increasing function. And here after 4 it's again decreasing. So using these facts we can now draw the graph of the function. Now, first derivative test. This test we'll use to define maxima and minima, extrema of the functions using derivatives now. In the previous lecture, we have studied relative maxima and minima, absolute maximum and absolute minimum using general definition. Now we'll find it using derivative. So here, suppose that x equals to c, it is a critical point, stationary point of f of x. Then, first condition, if here we have f of x, if it is greater than 0, f prime of x greater than 0. Look, we have point. Let me draw here. It will be more clear. For example, here we have point which is equals to c. Yes, this is critical point, our critical point. And now, the first order derivative should be, look now, neighborhood of this point. Now, on the left side, and first order derivative at the point c should be greater than 0. Here plus. And the right side of c should be less than 0. Here we have minus. Look, f prime greater than 0 on the left side of c, and on the right side f prime less than 0. So it means we are moving when passing point c from plus to minus. Is it clear? From plus to minus. So in this case, we call that x equals to c. It is the relative maximum. One more time. If we move from plus to minus, when we're passing this critical point, first order derivative, again, first order derivative, it will be relative maximum. And similarly, we can define relative minimum. Now it will be inversely. So here we have again this critical point c, and let's consider here left side and right side of c. So in the left side it should be now minus, should be negative. On the right side here, on the left side it should be minus, on the right side here it should be plus. So now when we're passing point c, we'll move from minus to plus first order derivative, the side of the first order derivative. In this case, we call this kind of point x equals to c relative minimum. Now here we have our extrema points using derivative. So if it is from plus to minus, relative maximum. If it is from minus to plus, it is relative minimum. So if it has the same sign on the left side and on the right side, so x equals to c, it is neither relative minimum nor a relative maximum. So if it's not changed the sign. Now, next example, let's consider it. So find and classify all critical points of the following function. So here it's given cubic root function, t times cubic root of t squared minus 4. So, and find here first order derivative. Here we have the first order derivative. It is equal to this function now. And now let's work with this function and find critical points, all critical points. To find all critical points, you need to equating by 0. Okay, no, now here we have how many critical points? Here we have 2, not 2 here, plus minus, and here we have 4 critical points. Because of here, you can see t is equals to plus minus 2. In this point, derivative doesn't exist here because it's in denominator. The denominator cannot be 0, but derivative cannot not exist, but it's also critical point by definition. Yes. So, and here also we have the next 2 points where the derivative is 0. So here we have 4 critical points. Now find intervals of increasing and decreasing here, and it's again we need to put to the f prime and define here plus and minus of the function. So you can see here it will be plus here when it is from minus infinity till minus 2, and from minus 2 till the this root square root of minus square root of 12 over 5, it will be now positive. Here it is positive. Now from this root to the second one, square root of 12 over 5, it is again positive here. Look, it's positive. Yeah. I mean here when it is because of here we have the power, and the power here is 2 or 3, so it should be now here it's negative. Sorry, here it's negative. Here it's negative. Positive, positive, positive. Here it is negative, and here it's again positive, and here it's again positive. Yes. So, and how many positive intervals? Here we have from minus infinity till minus 2. It is, you can see here the solution. From minus infinity to minus 2 it is increase, and from minus 2 till this root it's again increase here, and here it's again increase, and here it's again increase. So 4 corresponding intervals of increase, and then interval of decrease, here it's this one only. So in the middle. Yeah. Now, so here we have defined now intervals of increase and decrease. Now we need to study here extrema points. So extrema points, minus 2 and 2 are not relative minimum or relative maximum. Why? Because here at the point minus 2, it takes same size on the left side, on the right side. In both sides, it will be in same size, in same sign, plus, plus. And similarly, at a point 2, here again, plus and plus. But when we consider here, this one is, this one here is, it is this root. So minus with minus, minus 12 square root of 12 over 5. So this root, and in this root here we have, it's changed the sign from plus to minus, and similarly the next root. So here plus square root of 12 over 5, square root of it belongs to all of them. So here, and now here this root and this root gives us relative maximum and relative minimum. So the left, this one is relative maximum because it changed from plus to minus, and this one is from minus to plus. It is relative minimum. So this is relative maximum again. This one is relative minimum. And now So let's consider the graph here. So you can see here the graph of this function. And here also we can conclude that where is relative minimum and where is relative maximum. So here we have, this is the point of the maximum, and here it's point of the minimum. And you can see -2 and 2, it's not maximum or it's not minimum, but it is critical point, of course. But here the sign will not change. Now, next example with trigonometric functions. And here again find first order derivative and find here equating by 0, find all critical points, the given interval. And then again define here intervals of increase, decrease, and then you can see here after defining here we have plus in this root, here we have minus here we have plus again, here we have minus, and here we have plus. We'll check first order derivative, okay? So now after finding, so you can see here this is interval of increase, first one interval of decrease, increase, decrease, and increase again. It depends on plus and minus sign of the interval. So, and now here we can define maximum and minimum. So what is maximum and what is minimum here? If it is changed from plus to minus, it's maximum. If it is from minus to plus, it is minimum. If it's not changed, it's neither maximum nor minimum. So here we can say that relative maximums are the this minus this one, the first one, it is relative maximum, it is maximum. So, and this one also maximum, you can see from plus to minus, yes, this one also maximum, this is also maximum. And here we have minimums also, so this is minimum, relative minimum, and this is also minimum because it changed from minus to plus. Okay, so now we have found here all external points, and here we can see the maximum and minimums, exact values. And now the next definition here is concave up and concave down. Also we can define it like concavity and convexity, but to be simplified definitions, we can introduce here up and down. So here it is concave up. You can see this one is concave up. This is concave up, and here it is concave down, for example. So concave up and concave down. So to be similarity, so here we can say that a function is concave up if it opens up, and a function is concave down if it opens down, like this. Up, opens up and down. Or you can say it is convexity here down and convexity up by reverse order. So, and concavity and convexity are inverse definitions here. So now a function can be concave up and either increasing or decreasing. Similarly, function can be concave down and either increasing or decreasing. So here you can see it can be concave up decreasing, concave up increasing, or concave up decreasing, concave down increasing. Now, and now let's give the definition. Of course, when it's open down or open up, it's not a mathematical definition. So here we have mathematical definition. So given a function f of x, f of x is concave up on the interval I if all of the tangents to the curve on I are below the graph of f of x. And f of x is concave down on the interval I if all of the tangents to the curve on I are above the graph of f of x. So there is a more definition that we need to get at. The way a point x equals to c is called inflection point if the function is continuous at the point and concavity of the graphs changes at the point. So concavity, we need to change the concavity, for example, at this point. If here at x equals to c, it will change from concavity up to concavity down, for example, it will be inflection point. It's called inflection point. So, and here in this above definition, concave up on the interval I if all tangents to the curve on I are below the graph of f of x. Here also you can see, if we consider here some kind of tangent, for example here, yes, concave up it is. So you can see the tangent should be below. By the other side, if it concave down, tangent should be above the function. So here, using tangent, we can define concavity up and concavity down. And now, so here also you can see that in this graph, so all tangents will be below when it's concave up, and when it's concave down, all tangents will be above. Okay, now let's do it using derivatives again. So we have found here using derivatives extrema, and now we'll find using derivative concavity up and down. So given the function f of x, if now pay attention, second order derivative greater than 0, second order derivative greater than 0, it will be concave up. Concave up. So it will be which one? This one. If f, we can denote by this one, yes, concavity up. If it is less than 0, second order derivative less than 0, then it will be concave down, where all tangents will be above. So this means that using second order derivative, now you can define concavity up and concavity down. But we say that inflection point also, yes, flex point, or it's also called flex point, it's also called inflection point. So when it's not changing concavity up to the concavity down, for example, it will be again concavity up and concavity up when you move from this point. So it's not, it's called, if you change, it is called inflection point by this definition. If changed at this point. Okay, example now. Let's consider this example, and here you can see the derivative of this function h prime x. It is equals to 15x4 minus 15x squared. Yes, that's it. So, and now we can just factorize it, and it will be now 15 x squared. So here we have now x squared minus 1, it is x minus 1, x plus 1, and equating by 0. Okay, and now after equating by 0, we have 3 critical points. The first one is x equals to 0, x equals to 1, and x equals to minus 1. Okay, and now let's find here intervals of increasing and decreasing. So here we just put to the real line, and here we have now 3 points: minus 1, 0, and 1. Yeah, and now let's define intervals here. So, and derivative here, first order derivative, you need to check here it will be plus, here it will be minus, And here also minus, because of here x squared, even power, and here again plus. So now we have this kind of intervals, and where it's increase function, it increase here, here decrease, here also decrease, and here increase. Okay, so here now we have intervals of increase and intervals of decrease. Now let's find here maximum and minimum. So what is maximum here? X equals to -1 is maximum. Yeah, because it changed from plus to minus. And x equals to 1, it is minimum. Because of here, it changed from minus to plus. So it will be maximum and it will be minimum. But x equals to 0, it is critical point, but it's not extreme point, because here it cannot change the sign. Now, so we have, as we said, relative maximum and relative minimum. Now we need to find here, what should we find here? Second order derivative. And after finding second order derivative, let's find here second order derivative. And what is the second order derivative in this case? You can see here the result. So the second order derivative is equal to this one. And here, what kind of points we have? Again, here we have x equals to 0. X equals to square root of 1 over 2. Yeah, plus minus. So here, square root of 1 over 2. And x equals to minus square root of 1 over 2. So here we have 3 points again. Now they are not a critical point, they can be inflection point. So let's check now, is it inflection point or not? So here we have now put again to the interval. So if you put it to the interval, so here it is this one minus square root of 1 over 2. Here it is 0 point, and here it is 1 over square root of 2. And now let's try to find corresponding sign of the second order derivative. When you consider here some points, for example 1, your expression, this will be 60 minus 30, it will be positive. So it is positive here, it's positive. When you consider 0, what you have here, from 0 till this point. So here it will be minus. Here it's again plus, because of here we have only first degree in this inequality, and here again minus. And now we said that when it is concave up, when it is concave down, let's return to the definition. If second order derivative greater than 0, it will be concave up. So in our case, where is second order derivative greater than 0? When here it is from minus square root of 1 over 2 until 0, and from 1 over square root of 2 greater and plus infinity. Here until plus infinity. Here we have concave up. And concave down, similarly in where is minus. Here we have concave down. In this interval, and in this interval also we have concave down. So here also we have the solution. As we said, it is concave up here, and here we have concave down. So, and now by this way we have found here all points where it can be concave up or concave down. And now what is the flex point here, inflection point? Do we have inflection points? Of course we have inflection points. So where 0, all points here are inflection point, because you can see in all points it changed the sign. There are no point where it not change the sign. So here point minus square root of 1 over 2, 0, and 1 over square root of 2, it is inflection point. Okay, they are inflection points. And here now we have the graph of this function. So here we can put now, we can find here maxima, minima, which we have defined here, and also concavity up and down. So now second derivative test. We have studied first derivative test, and now there is second derivative test also we have. Suppose that x equals to c, it is a critical point. F prime c such that f prime c equals to 0, and that f second order derivative is continuous in the neighborhood of x equals to c. Then look, first order derivative there exists and it's equals to 0, it is 0, and the second order derivative continues in the neighborhood of x equals to c. X equals to c, it is critical point. Now if, look, second order derivative at this point less than 0, then x will be relative maximum. If second order derivative here greater than 0, it will be relative minimum. So by this way we can define now easily using second order derivative extrema. Is it absolute? Is it relative maximum or relative minimum? Of course, if second order derivative equals to 0, then x equals to c, it can be relative maximum, relative minimum, or nada. So which is not gives us exact result if second order is 0. So we need to continue here. If it is 0, we need to continue, find third. If third one equals to 0, and find fourth one. So it should be even order derivative, it should be different from 0. If even order derivative different from 0, then you will consider here, if it is negative, it will be maximum. If it is positive, it will be minimum. Is it clear? So if it is less than 0, it is maximum. If it is greater than 0, it is minimum. In this case, it depends on the second order derivative. Okay, now it's the graph of x4. It has relative minimum at the point x0. Why? Let's check here. So f of x is equals to x4, and find first order derivative. So the first order derivative will be 4x cubed. After equating by 0, if we need to find critical point, yes, here. So here we get x equals to 0. And now let's define second order derivative. So the second order derivative here, it's, how much is it? It's 12 x second. Yes? So when you put again here instead of x 0, you get again 0. But also you can say it's always positive. But here it will be 0 again, yes? After finding f double prime 0, it is 0. And now find third order derivative. What is it? It is 24. Yeah, it is 24x, and which is again 0. When it is 0, it's again 0. And now we have the fourth order derivative now. If you find fourth order derivative, it will be just 24. It's just 24, which is greater than 0. So you can see here, after finding first order derivative, I said it should be even order derivative, different from 0. So, and we can say it is greater than 0 using definition. If it is greater than 0, it will be relative minimum. So now conclude. X equals to 0, it will be relative minimum. I think it's clear now. And also similarly, you can see minus x fourth. So if it is minus x fourth power, so it will be when you find here until first order derivative, you get now negative value. It's like minus 24. So if it is minus 24, it will be now less than 0. And if less than 0, it will be relative maximum. And similarly, here we have x cubed. If x cubed, in this case, when x equals to 0, second order derivative is 0 again, and not gives us exact result. And that's why at the point x0 had neither relative minimum or relative maximum. Now here, use the second derivative test to classify the critical points of the function. So here we have second order derivative. It is equals to 60x cubed minus 30x. And then we have considered this kind of example. So, and here at the point minus 1, it is minus 30. At the point 0, it's 0 again. At the point 1, it is 30. Now it means that this is greater than 0. This one less than 0. Yeah, and at the point 0, it's 0. We cannot define here. So, but here we can define. That's why we can just say that at the point x equals to minus 1, it will be maximum, relative maximum. And here it will be relative minimum. Relative minimum. Using second derivative test. Now, next example. Here, almost same. Here we have two critical points. And you can see here, after finding corresponding value at this critical point, we get here this kind of negative value, which means that the point 3.6 for this function will be relative maximum. And a 0.6 here, and at the 0.6, what we have here, if you put 0.6, we cannot define here because it will be there are no information. The 0.6, because 6, when you put 6, but here it can be defined by the first derivative test. So if you put the first derivative test, in this case it cannot be 0 because it's in denominator here you have. But if you put it here, we will not be able to use second derivative test for the 0.6. That's why we'll use here first derivative test and define here signs, corresponding signs. Here it is plus. In this interval it's minus, and here again plus. So you can see here 6, it is relative minimum. So 3.6 it's relative maximum, and a 0.6 here is relative minimum. Okay, now here let's find now second order derivative. And if you find here second order derivative, you get here this kind of expression again. So, and now here we can classify the points again using now second order derivative. So find inflection points and find maxima and minima here. So if it is less here, it is minus. Here it's again minus. Here it's now plus. So you can see here this point 6.6, it is not inflection point, but here 0.7.2 here 7.2, it is inflection point because it changed from minus to plus. And where it's concavity up and concavity down, you can say, so it changed the concavity here, the 0.7.2, and here we have concavity up and down. Where it's up and where it's down, here again we need to use the above definitions. So here, and then we can say that f prime double prime greater than 0, it will be concave up. F double prime less than 0, it is concave down. So here we have two intervals of concave down. Here we have two intervals of concave down and one interval of concave up. Here down, here down, here up. Down, down, and up. Okay, so now let's sketch the graph. And we have defined here 6, it's relative minimum. And here we have relative maximum also, this point, yes, 3.6. And we get this kind of graph of this function. If you have any questions, you can write on comments. So in this graph, we will finish today's lecture. Thank you for attention.